Welcome, welcome, one and all, to the last new lesson of the semester. Today we're going to look at means and variances of random variables. So what's a random variable? Well, rolling a die, for example, is a random variable. Flipping a coin is a random variable, right? Obviously, you would keep track of some, like the number of heads or how many times you rolled the number 4 or something like that, but those are random variables. Okay, so let's start with an example. Let's say you're going to play the most exciting game ever imaginable. You roll a 4-sided die and you bet $1 on the roll. If you roll a 3, you get $10. Okay, so what's the expected value of this game? Okay, meaning on average, how much would you win or lose per roll if you played this many, many times? Okay, so this situation illustrates what we would call a random variable. Okay, although I cannot predict the very next roll of the die, I can tell you if this game is played many, many, many times, what the average result will be. Okay, so pause the video here for a moment. Historically, a lot of my students are able to figure this out on their own just using a little probability and common sense. Okay, so I'll kind of go over the way some of my students approach this problem, and it should hopefully make things make sense to you. So some students would say, well, it's a 4-sided die, right? So I could roll a 1, a 2, a 3, or a 4, right? And they're all equally likely. So each one of these will happen 1 out of 4 times. Okay, when I roll the 1, I'll lose $1. When I roll the 2, I'll lose $1. When I roll the 3, I'll make $9, right? Because I paid $1 to play and then I get $10. When I roll a 4, I lose $1. And they'll say, okay, so if I play the game 4 times, many, many, many times, right? The average result would be winning $6. But that's for 4 rolls. So the average result would be $1.50 of winnings. Net gain. That's why it's such an exciting game. If any casino actually offered this, you could go play this for a living, right? Because on average, you would make money. And there you go. That's a perfectly kind of acceptable, common sense way to do the problem, right? Just basically created the sample space, and then each outcome in the sample space has some monetary value, right? Lose $1, lose $1, make 9, lose $1. And since they're all equally likely, I just added them up and then divided by 4 because there were 4 equally likely outcomes. Okay, now here's how we typically do a problem like this. Okay, rather than listing every outcome of the die, we define a random variable to be the amount that you win or lose on a play of the game. If I define that random variable, now there's only 2 different outcomes, right? Win or lose. Okay, I'm going to win with a 1 in 4 probability. I'm going to lose with a 3 in 4 probability, right? Now, if I just take whatever the outcome is, multiply it by the probability, and then take the sum of that, right? It's the same exact process. It's just a little faster. Right? So instead of having 4 things, adding them together and dividing by 4, right? In this case, I just had the 2 things. Multiply it times the probability and add them together that way. Okay? So hopefully you can see that this is really the same exact process. It's just a little streamlined. So it's basically, whenever you come across these random variable problems, make a table. List your outcomes of your random variable. Put a column where you put the probability. And notice what I did here. I made sure, right, that the sum of my probabilities is 1. That's really important because that's where students mess up. If the sum of the probabilities is greater than 1, you've messed up. If the sum of all the probabilities is the column is less than 1, you've left something out, right? So just always double check, make sure the sum of your probabilities equals exactly 1. Multiply across, and then again, take the sum, and that's the average per play right there, because we've already multiplied it by the probability, or in other words, basically divided by 4. And there you go. That's how we can handle the expected value or mean of a random variable. Title of the lesson, right? Okay, so as we said, on average, and that's key, on average, we would expect to win $1.50 per roll over many, many rolls. Really important to understand, if I play the game once, could I win $1.50? No, it's not even possible. If I play the game once, I either lose $1 or I win $9, right? This is the average result. So this happens after many, many repetitions of the random variable. Okay, so that's really important to understand. The mean of the random variable doesn't have to be something that occurs in the sample space, right? It's the average of many repetitions. Okay, and please don't round it off. Rounding it off would be incorrect, right? Because again, it's the average of many repetitions. Okay, so here's what we just did, right? When we have a discrete random variable, we can list out all the outcomes of the random variable, list out the corresponding probabilities, and then we simply multiply the outcome and its probability and take the sum. And there you go. That is the mean of the random variable. And this is the notation that you can use. Mu, right? Mu is the theoretical mean. It's the population mean. It's the exact mean of the population, right? It's not, we didn't actually do this. We didn't actually roll a die over and over again, right? This isn't simulated. It's not estimated. It's the exact answer. And that's why we can put mu, because remember, mu is a population parameter, and this is a parameter. Okay, it's not something we observed. It's something we calculated exactly. Now, this formula is, of course, on your formula sheet. Here's how it appears on the formula sheet. It's labeled capital E of x for expected value of x. It's also labeled mu sub x for the distribution's theoretical mean of x. And there you go. It's the summation of each x value multiplied by its corresponding probability. And so here we are on our formula sheet, right there. For a discrete random variable, x, here's the mean. Okay, so the expected value, that's a synonym for the mean of the random variable. Expected value means mean. Okay. All right, now let's talk about the variance or standard deviation of the random variable. Going back to what we said way back here, right? Let's take the variance of this data set, right? -1, -1, 9, -1. Okay, so step one would be find the mean, which we already did, right? The mean's $1.50. Now finding the variance, hopefully you guys remember that. You would take each value, so -1 minus the mean. Right, you got to sum this all up. Right, hopefully you remember that. And then you're going to divide that. Okay, and this is not a sample, right? This is a theoretical, so that's why we would divide this by n. In other words, 4. Okay, there's our variance, and then square root that would give me my standard deviation. All right, let's see if we can do that real quick. What is that? 3, 5. By the way, this is a shortcut. When you, of course, have repeated addition of the same thing, you can turn that into 3 times, right? Times that. Again, there's your variance. Okay. Now, notice at this point, if I wanted to, I could break this up, couldn't I? I could say that's 3/4 and 1/4. And there you go. That's the formula for the variance. If I square root that, I would now have the standard deviation. Okay. So I took the formula for standard deviation that I already knew from chapter 1, and I've just written it in a little different way. Right? Notice 3/4, that's the probability of losing $1. 1/4, that's the probability of winning $9. So writing it that way brings me to this formula on our formula sheet. Okay? We take each outcome minus the mean squared, right? The first outcome minus the mean squared. There's a second outcome minus the mean squared. Okay? And we multiply each one of those outcomes with its corresponding probability. So this happened 3/4 of the time, that happened 1/4 of the time. So it's not really a new formula, right? It's just the same formula. We've just kind of changed the way it's written because when we talk about random variables, we talk about the probability of each outcome. So it's just easier to think about it this way as opposed to, writing out a bunch of outcomes or making a data set. Okay, so there we go. That's what we just did. There's a variance, and of course, yay, square root of variance is standard deviation. And again, notice it's labeled with sigma sub x because, again, this is theoretical. This is a parameter. Okay, this did not come from sample data, right? We didn't actually roll the die. This is the theoretical result of many, many, many rolls. All right. Let's try a problem now. So let's say we do a little experiment. We take a bunch of kids, and one at a time, we put each child in a room with 5 toys. We watch the child for a fixed amount of time, and we record how many of the toys the child plays with. This is kind of a famous experiment that child psychologists would do. They were wondering if something like this could be used to predict a child's intelligence later in life. The thought was, kids that just sit there and drool on themselves and don't investigate any of the toys, that these kids here may not be so bright, right? And then the kids that investigate more toys and are more curious, that they would go through life and become, more intelligent adults. So this is a kind of a famous experiment. So anyway, these are the results of one such experiment. 3% of the children just sat there and drooled on themselves, right? 16% just played with one toy the whole time. 30% tried out 2 toys, so on and so forth. Okay, so let's try our new formulas. Let's calculate the mean of this random variable, right? The number of toys that were played with, that's the random variable. And let's also calculate the standard deviation of this. Okay. All right, so I'll just go to the next page if it worked out. All right, so step 1, the mean. We simply take what we have here, 0 times 0.3 plus 1 times 0.16 plus 2 times 0.3 plus 3 times 0.23 plus 4 times that plus 5 times that, right? And we get these numbers, we add it up, there's our mean. So the average number of toys played with, 2.68. And again, no single child could play with 2.68 of the toys. Can't happen, but that's okay. This is the average of all the subjects, right? An average doesn't have to be found in the sample space. All right, Now let's do our, right, that was this one. Let's do our standard deviation formula. Okay, so we're going to take each one of the results, 0 minus the 2.68 squared times its probability, and add that to the next one. Right? So 0 minus that squared times its probability plus 1 minus, again, the mean squared times its probability, on and on and on, so on and so forth. There's our variance, and there's our standard deviation. And voila, we now have the mean and the standard deviation of our random variable. Okay, so hopefully that's pretty nifty. All right, that brings us to a fairly important concept in statistics: the law of large numbers. I've kind of been saying this indirectly over and over again, so now that I'm going to show you the actual law of large numbers, it should hopefully make sense. Okay, the law of large numbers says if the mean of x, or x bar, is an unbiased estimator of mu, right? So we're using correct techniques, so we have no bias in our data collection, then x bar will approach mu over many trials of an independent event. So that's what I've been saying over and over again. If we do this many, many, many times, this is where we're headed, right? So if we do it many, many, many times, the mean that we observe will target or approach the true theoretical mean. And that's all the law of large numbers says. So pretty straightforward. I think that makes sense to everybody. But it does beg the question, over many trials. Well, how many is many, right? What's a large number of trials? How many do I need to do for x bar to approach mu? And this is the kind of question we kind of grapple with a lot in statistics. How large of a sample size do I need? How many trials, right? Well, I can't give you an answer that works for every situation because it's always going to depend on the situation, right? Things that are higher variability will require more trials, right? Things that are lower in variability will require fewer trials. For example, think about flipping a coin. There's 2 outcomes only. Each is 50-50. That has the lowest variability. So to figure out the average number of heads or the average number of tails for a given number of flips, you won't need to repeat it as many times as, say, trying to figure out the likelihood of winning the lottery, right? Winning the lottery is a very small probability. So you would have to simulate that or actually buy tickets, right? Many, 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 many times before you get close to the true average result. Okay, so as you have more and more outcomes, as you have outcomes that are more rare, right? That increases variability. And so that means you would need more trials for your x bar to approach your true population parameter. All right, let's get into our rules. We've actually talked about these before. I want to say it was maybe chapter 2. Here's the first rule for means. If x is a random variable, a and b are fixed numbers, constants. Okay. Then if I take the mean of our random variable multiplied by something, right, and then added, something added to that. Okay. I can just take the mean of the random variable multiplied by the multiplier and add it to, again, the same constant. Okay. We'll illustrate this in an example in a minute, but we talked about this in a previous chapter. Hopefully it's ringing a bell. Okay. Second rule, if I have 2 random variables and I want to find their sum, right? The mean of the sum is equal to the sum of the means. And again, that should hopefully make sense to you, but I have an example we'll go through to illustrate this in a second. Okay, so let's look at those examples. All right, let's say you're doing a fundraiser and you're going door to door selling candy bars. So obviously this is a historical example, right? Now that we have COVID lockdowns every which way, you probably can't do this, but pretend it's still 2019. So you go door to door. You're selling candy bars as a fundraiser for your sport or musical production, drama, whatever it is. And being a good statistics student, you keep track of your results. Okay? And it turns out 50% of the time you sell one candy bar when you knock on a door. 30% of the time you sell two, and 20% of the time you sell three. Hey, notice that adds up to one. Hey, that's everything. So clearly you're an excellent salesperson. You never take no for an answer. All right, so step one, let's just find the mean of this random variable x. So remember our formula there, it'll be 1 times 0.5 plus 2 times 0.3 plus 3 times 0.2. There we go, our mean is 1.7. So on average, you're selling 1.7 candy bars per home visited. For fun, let's find the standard deviation. Okay, so standard deviation would be 1 minus 1.7 squared times 0.5, right? Plus 2 minus 1.7 squared times 0.3, plus 3 minus 1.7 squared times 0.2. Add that all up and square root. And voila, there you go. There's the standard deviation of the number of candy bars you would sell per home visited on the average of many homes. All right, now let's take another random variable. Let's say your friend is doing a fundraiser for their organization, but instead of candy bars, they decide to sell suckers. But your friend is also an excellent statistics student and keeps track of their results. And here's their distribution for their random variable, sales of suckers. 10% of the time they sell 4, 40% of the time they sell 5, and 50% of the time they sell 6. Wow, is your friend a great salesperson, right? Maybe it's because suckers are cheaper, or maybe your friend really likes suckers, and anytime somebody doesn't buy enough, your friend grabs a few and starts, eating them themselves, and then they have to pay for them, right? All right, so again, let's calculate our mean and our standard deviation. So 4 times 0.1 plus 5 times 0.4 plus 6 times 0.5. There we go. Mean number of suckers sold, 5.4. Okay, standard deviation, 4 minus 5.4 squared times 0.1. 5 minus 5.4 squared times 0.4. 6 minus 5.4 squared times 0.5. Add that all up and square root, and there you go. Standard deviation of the number of suckers sold, 0.66. Again, this is assuming you're looking at many, many, many homes visited. All right, so now here's where our rules will come in. Let's say the profit per candy bar sold is $1. The profit per sucker sold is 50 cents. Okay. Now, let's say that both candy bars and suckers are offered for sale at the same time. So your friend decides to take over, or you decide to take over and share the profits, right? Maybe, who knows, you're working for the same goal, right? Well, what's the total expected profit now per home visited? Okay, so in other words, we're combining the two distributions. Okay, so here's our rule. We're going to be taking the mean of x, which is 1.7, right? And it gets multiplied by $1. Okay, so that's how much money you make per home visited on candy bar sales. Now, for random variable y, suckers, you're only making 50 cents per candy bars sold, but you sold on average 5.4 of those. So 5.4 times 50 cents. There you go. We just illustrated our rule for combining random variables and also the multiplication. Okay, I didn't demonstrate adding a fixed value to each one. Here's how I could demonstrate adding a fixed value to each one. Let's say the generous Irvine company decides for every sucker you sell, they will donate 25 cents. Okay, well then all of a sudden we would add 25 cents per sucker sold. And that would be the A value in that formula. Okay, so anyway, work that out and you would get on average $4.40 per house. Okay. All right, that's the rules for means. Let's move on. Let's look at variances. Now, most students do well with the means. Variances are where I notice students sometimes struggle. Again, we actually went over the first rule previously back in, I think it was chapter 2, when we did linear transformations of data sets. Okay. And what we said was, if we add something to every value in a data set, or in other words, add something to a random variable, it has no effect on measures of spread, right? We said it just picks the graph up and shifts it. It doesn't change, it doesn't shrink it, stretch it, doesn't change the spread. And so adding has no effect on variance or standard deviation or any measure of spread. Okay, but multiplying does, right? If I multiply, I stretch it if that multiplier is, of course, greater than 1, right? If I multiply by a fractional value between 0 and 1, now I'm going to shrink the spread. And the rule is, for variance, right, whatever our multiplier is, well, it will multiply the original variance by that multiplier squared, which makes perfect sense. And again, we went over this back in chapter 2. Okay, and if you don't believe me, just make up a set of numbers, right? Make up a data set, calculate the variance, then go back, add something to every value in the data set and recalculate the variance. You'll get the same thing, right? Then go back and take that original data set, multiply it by something, calculate that new variance, and sure enough, you'll see the new variance would be the old variance times the square of your multiplier, whatever your multiplier is, other than 0. Okay, let's look at the next rule. Here's where students struggle. Okay. Most students get the first one. Okay. If x and y are independent random variables, okay, there's going to be a different rule for dependent, by the way. If they're independent random variables, and I want to take the variance of the sum of the random variables, well, that's equal to the sum of their variances. Okay, that makes sense. Just like the rule for means. But here is where students really scratch their head. What if I want to take the difference of two random variables? Okay, the variance of the difference of two random variables is actually the sum of their variances. Whoa, that's mind-blowing, right? All right, let me see if I can set a little something up here to try to explain this to you the best I can. So let's see if I can follow along with a quick experiment here. All right. I have some measuring cups over here. All right, so let's say that I'm a highly trained pourer of liquids with these particular measuring cups. And I've done it so many times, I can tell you how accurately I pour. So anytime I try to pour into this measuring cup, I'm always within 10 milliliters of my target, okay? So here's what I'm gonna do. I'm gonna attempt to pour 500 milliliters into this measuring cup. Deep breath. All right, here we go. the meniscus. Oh, needs a little more. There we go. Beautiful pour, right? Beautiful pour. Wasn't that exciting? Okay, now I attempted to pour 500 milliliters into this, right? Now, here's the big question of the day. How much water is actually in this measuring cup? Is it exactly 500 milliliters? Maybe, but we can't guarantee that, right? We can say, remember I told you I would be within 10 milliliters, right? Okay, we can say that. That measuring cup has 500 plus or minus 10 milliliters in it. All right. Now, here's what I'm going to do next. From this measuring cup, I am going to pour into this measuring cup. And I'm going to try to pour 200 milliliters into this measuring cup. Okay? And again, I have that same ability that I'm going to be somewhere around 200, but I can't guarantee I get exactly 200, right? No one's perfect. So here we go. And stop. Whew, another beautiful pour. Okay. So now, if I went for 200 milliliters and I'm always within 10 milliliters, the amount of liquid in this measuring cup is right? This measuring cup has between is 200 plus or minus 10 milliliters in it. Okay. Now here's the light bulb moment. Ready for this? How much is left in that measuring cup? Right? That measuring cup started with 500 plus or minus 10 milliliters. Then I subtracted 200 plus or minus 10 milliliters, which means what's left in this measuring cup would be 300 plus or minus 20 milliliters. Mind-blowing, right? Even though I subtracted, the variances still add. Because it's not the act of addition versus subtraction, right? It's the act of doing whatever it is I'm doing that creates the variations. Every time I pour, I'm creating air, right? I'm creating variance from one pour to the next. And that's why when I subtract random variables, I still add their variances. Okay, so hopefully that makes sense. All right, walking back around, and hopefully you can read that. Okay, so again, try to remember that one. That one's commonly messed up because it's a little counterintuitive to think, hey, I'm subtracting, but I still add the variances. Okay. All right. And here's rule 3. This is when I have dependence, right? When two variables have a correlation, that means there's dependence here, right? They're related in some way. One's dependent on the other's outcome. So when I have that dependent situation, here's my formula. Rho, by the way, rho is the theoretical correlation. Remember we had R, right? We said correlation was R. Well, that's the statistic. R is the statistic. Rho is the parameter for correlation. Okay. So you'll be tipped off when to use this formula by the fact that rho is given in the problem, right? Otherwise you can't do the problem. So that's pretty obvious. Oh, I need to use the formula that has rho in it. All right. Let's go back to the start of the lesson. Exciting game of chance. We rolled that 4-sided die, we bet $1, etc., and so forth. Okay, I'm going to show you another way to do that problem, the way that I did it when I took statistics, because when I took statistics, two things. One, we didn't have formula sheets, and two, we weren't allowed calculators. So I'm going to show you kind of the old school way of doing this problem just for fun. So here's how I would have done the problem. Again, I would make my table, right? Outcomes of the random variable, column for the probabilities, multiply them, take the sum. Okay. Over here, again, this is just finding my variance, right? But notice, this is the cool thing. I could have done x squared times the probability of x, right? And then subtracted the mean squared, and I get the same thing. Okay, so kind of a cool little trick if you want, right? But that technique, that formula is not on the formula sheet, and you guys have a calculator at your disposal, so you'll probably never do it that way. But anyway, just a side note, how we did it back in the day, because the reason why is it's a lot easier to do x squared times p of x than it is to do x minus the mean squared, because the mean oftentimes is, fractional. So now I'm squaring some pretty nasty numbers here, whereas over here these are usually pretty easy to square. So if you didn't have a calculator at your disposal, that technique's a little easier. All right, let's do one more problem. Again, going back to that exciting game of chance, let's say you're going to play the game exactly twice. Okay, so somebody plays the game 2 times. What would the mean of those 2 plays be? How much would they expect to win if they played the game twice? Not per play, but twice. Like, what's the total, the net for the 2 games? Okay. Well, you could use the formula that we just went over, right, for the sum of random variables. And it's simply take the sum, 150 plus 150. $3 would be the average result. But again, you couldn't actually do that if you were to only play the game twice, right? This is the average of playing the game twice if you play the game twice many, many, many times. Okay, kind of an interesting thought. And now let's do the standard deviation. So again, well, actually, let's just use our formula, right? So our formula says we would just add the variances. So the variance we just did on the previous slide, 75/4 plus 75/4. There's the variance of 2 plays. So the standard deviation of 2 plays would be that. Okay, pretty fun. You can just confirm this the old school way. I'll let you do that on your own if you want. So do it the long, slow way. In other words, make a list of all the possible outcomes of X, right? Losing twice, winning once, losing once, and winning twice. Assign a probability to each and calculate the mean of that distribution. You will get $3. Find the variance of that distribution. You will get 75 halves. Okay. So you can confirm that on your own, but you can also see that this is much faster, and this is the whole idea. Sometimes they might just tell you the mean of the random variable. They might just tell you the standard deviation or the variance of the random variable, and then do something to it, like say, oh, play the game 3 times or 5 times, whatever. It's much easier to use these shortcuts in those scenarios. Last point I want to make, and I really want to stress this, we have rules for variances. We have rules for variances. These are not rules for standard deviations. I'll say that again. We have rules for variances. These rules are not for standard deviations. Okay? So that's crucial. Because notice, for example, what if b were a negative number, right? A lot of students will say, I'll just multiply b times my standard deviation and I'll get the same answer. Not if b is negative, you won't. right? You'll get a negative result. And same thing when you're adding these guys. Okay. And also 0 can come into play and mess you up too. So the idea here is always go to variances, use your rules for variances, and then when you're done, use square root to get your standard deviation. Okay. Follow those steps, you'll get them right. Start playing, loose with those steps and trying to combine standard deviations, and you will potentially make mistakes. So please never combine standard deviations. Always go back to variances, use the rules for variances, and then square root to get back to standard deviation. Okay. All right, ladies and gentlemen, we are now done with material for this semester. I hope you enjoyed this semester, and I hope you're ready for your Chapter 7 test and for your final. Good luck.